Building a distribution function for the damage impact. Admittedly, building a distribution function from scratch requires creativity and using certain techniques that merge elementary distribution functions from at risk in order to create a customized one. All we know, again, is that, in the mind of the farmer, she pictures damages to her crop in 4 imaginary buckets: a low damage up to $20,000, a moderate damage anything from $20,000 to $50,000, a high damage anything from $50,000 to $100,000, and a catastrophic damage anything beyond $100,000 all the way up to damaging her whole crop for $500,000. This is highly subjective, obviously. Any other neighbor farmer would see their damages into any different number of categories with different intervals each. It is also highly subjective, but necessary, the parallel task of assigning probabilities. In other words, answering the question to herself, how likely is it that any one of these 4 states of nature might appear? In her mind, she assigns the following probabilities: 20% probability of relatively low damages, 60% probability of a moderate one, 15% chance of a high damage to her crop, and, finally, only 5% probability of a catastrophic damage. Now, we have all the elements required to build a damage distribution function as follows. 1. On range C2:E5 on the Parameters and Results tab, fill in the proper information with respect to ranges and probabilities. 2. On cell E6, create the following discrete function that chooses alternative ranged x values according to respective p probabilities, equals risk discrete A2:A5, E2:E5. This function creates the following probability chart. 3. Driven by this function, write in C6 the following index function that will respectively retrieve the chosen minimum parameter as follows, equals index C2:C5, $E$6. 4. Copy this cell to D6 to retrieve the chosen maximum parameter equals index D2:D5, $E$6. 5. With these functions in place, we are now able to create a function on top of cell B6 that changes its parameters being driven by the risk discrete function in E6 and their respective min and max parameters on C6 and D6, equals risk uniform C6, D6. 6. Declare cell B6 as an output with the Add Output button in at risk with the name impact. Cell B6 should now look like this. Equals risk output impact plus risk uniform C6, D6. 7. At this point, we will simulate some 10,000 iterations for this previously declared output cell to see its shape. After the simulation is performed, the following chart may be shown. One useful feature present in at risk is the ability to fit a distribution based on previous simulated results. Use the fitting button on this same window for at risk to choose the best distribution that fits your 10,000 simulated data points. Go to the second tab Distributions to fit and make sure that the lower limit fixed bound is fixed in 0, not allowing for negative numbers, and all distribution functions are selected, as shown on the next window. Click on Fit for at risk to look for the best distribution according to defined parameters. According to the default fitting criterion, AIC, a Daigum distribution function allows for the best possible fit to the data. Click on Write to Cell to eventually get this distribution function back in Excel. When this window appears, click on Next, as we do not want to change any parameters here. Place fitted distribution function on top of cell B8. Therefore, this cell will now contain a Daigum distribution function that looks as following. Equals risk Daigum 0.46821, 2.6831, 0.5560, risk name impact. 8. Write these parameters into range B9:B12 to make a rapid reference of them if they need to be changed somehow in the future. Also, on cell B13, write the upper boundary on this distribution, maximum damage for total crop. 9. Now, we are ready to rewrite the Daigum function on cell B8 as a referenced function to these parameters and with the inclusion of the upper truncation and its proper definition as an output cell, as follows. Equals risk Daigum B9, B10, B11, B12, risk truncate B13, risk name impact. 10. After a simulation has been performed, this Daigum output function should render the following distribution. In summary, we have transformed the farmer's subjective criteria involving her assessment of damages into a probability function that can now be used to create a stochastic decision tree analysis model.